So the first idea I want to look at here is just solving these sorts of questions where you want to show that the left-hand side is greater than the right-hand side, that sort of thing. Now, a tactic we often use is rather than trying to do that, it's a lot easier to move everything to one side. In this case, I've moved it to the left. So we end up with left-hand side minus right-hand side is greater than 0, because clearly if I can show that, then once I know that to be a fact, then I can move the right-hand side over and I've proven left-hand side is greater than the right-hand side. Now why do that? Because the number's 0. You see, finding where something changes from positive to negative, that is of course 0. Well, if you think of the graph, so think of it as a picture, what happens when it changes sign? Well, either it's going to be an x-intercept, so it's equal to 0, or it'll be undefined. It might be an asymptote, and then it jumps from positive to negative either side of the asymptote. But one of those two things must happen. So looking at the critical points of the domain, those boundary values, then allows you to solve these sort of questions. A reminder of how we write our interval notation using the brackets. So the square bracket means the interval endpoint is included. The parenthesis is it's not included. Something like that, where both ends have got brackets when it's a closed, because all the endpoints are included, whereas something like that would be open. None of the endpoints are included. And then we have what's called unbounded, if the interval goes out to infinity or minus infinity, I suppose, the other way. So if I had something like x is greater than 5, which would look like that on the number line, then that is an open, unbounded interval. And in interval notation, we write it that way, 5 infinity. And it also means in set notation, we write x such that x is greater than 5, remembering the colon stands for such that. And less than or equal to 6. In this case, we have a closed, unbounded interval, and we would write it that way. In between 2 points, but both of them here are open, so it's an open, but it is bounded. We have got endpoints there. And this one here, it's bounded as well, but this one's closed. Ooh, this one where one's open and one's closed. So what do we call that one? We just call that bounded, because closed, open, well, it's not really satisfies either. So it's just bounded. There's one where there's 2 bits. So that is simply the union of 2 different intervals. That way. Okay, so that's a recap on some notation. Composite functions, another thing we looked at. So when we combine a couple of functions together to create some new function. So the notation, this means I'm substituting g into f, but another way of writing it is fog. It's not really an O, but it looks like an O, but fog. So if these were my 2 functions, then fog of x would be when I'm substituting in g into f. So everywhere I see x, I'm replacing it with 1 on x squared, and I can play around with that, and I get 2 on 4x squared minus 1. Whereas if I go goff, it's not necessarily going to be the same thing. So this time, everywhere I see x, I'm replacing with 2x on 4 minus x squared, and we'd end up with that, 4 minus x squared over 4x squared. Okay, let's go to actually solving then an inequation. So we have something like this. Sure, one technique would be to draw up the picture and we can have a look. When is it always? Well, in this case, below the axis. But if I use the critical points idea, because we notice we've got 0 on the right-hand side, when would it change sign? Well, in this case, it would be the x-intercepts, which would be 1 and -3. Once I know those boundary values, I just have to test areas and see where we are. And it turns out with this one, we're to the left of -3. On the right-hand side, it's just the single point, x equals 1. So the solution to this is x is less than or equal to -3, or that single point of x equals 1. That brings us to these sort of ones, the pronumerator and the denominator. And we've already seen a few ways of doing this. So here's yet another. Another approach would be to move everything to one side and create left-hand side minus right-hand side. So we have this. Well, it's an algebraic fraction, so let's make it an algebraic fraction. And I now have -13 minus 5x over x plus 3. But now's when I think about it and say, well, the only time this could possibly change sign is either at an x-intercept or a discontinuity. So if I'm saying, where's the x-intercept? If I've got a fraction equaling 0, it must be the top of the fraction that equals 0. So I know, therefore, minus 13 on 5, that would be a solution to the top equals 0. The other time it could change sign is at the discontinuity. Well, with a fraction, that's where the bottom of the fraction equals 0. So the other one is negative 3. It's another way of finding those two critical points. Test the different areas, and I'm to the left of negative 3, but I'm also to the right of minus 13 on 5 for this one. So I think that brings us to, is it our fourth way of solving these or fifth way of solving these? We've got a few methods now of how we can do that question. Okay, so 3A is what we shall do.